So what is it? A tensor. Well, a tensor is a multilinear map on these vectors, on covectors. But I'm not going to write it in, well, with all generality. I just write the components. A tensor is something that will have, well, let's say tensor of type PQ will have kind of P indices upstairs and Q indices downstairs. So a tensor is a geometric object which has those components. So each index goes from 1 to n, right? And there are that many of these indices, so there are that many components which all depend, these are functions of x. And they have to transform, when you change variables, they change according to that rule, ij, let's call it k1, kp, and this l1, lq. Basically, they transform like all these upper indices, we call them contravariant indices, transform like vectors. And all lower indices transform like covectors. So basically what you have here is something like well, because there is no space. So those will give me this. So you get I1, IK, and this is K, oh, this is P. K1, KP. You see, these are the ones that are exactly like this, but there are just P of them. And these ones will, well, this should be, this whole thing should stay right here, just don't have space there. So that will look like this, L1, LQ, and JQ. So the tensor is a geometric object whose components transform this way. It's a direct generalization of vectors and one forms. Remember that this was motivated by the chain rule from the partial derivatives and differentials. Okay? So that's a tensor of type PQ. What is P? P is the number of, kind of, if you want, vector-like indices, and Q is the number of one form or covariant indices. Okay? So then, what is a K form? A K form, well, let me say just a tensor of type 0Q. So that it doesn't have any upper indices. So that it only, it doesn't look like the vector, it only looks like one form, but there are more one forms. So it will look like this. T I1, IQ, dx I1, dx IQ. So that's, well, because there is sum of all the i's. So these are the components, these are those differential, that's a tensor product. Okay, so basically these are the components, and that is, it transforms like this without those, so without that part. So this is an arbitrary tensor of type 0Q. And now the K form is a tensor of this type, which is in addition antisymmetric, which basically means that when you replace the position of any two indices, it changes sign. So, well, let's call it Q1. Well, usually they're denoted by Greek letters. So what would be, well, it's something like this. And then we have dxi1. Well, you see that I introduced that. What is this? Well, that's called extruded product, or wedge product. This is a tensor product. So what is it? Well, basically it's an antisymmetric tensor product. Antisymmetric tensor product. Well, which means that if you take the components, well, let's say there's an index J and then an index L, then if you take any two indices and interchange, then it will change sign. So I just switch this, then it changes sign. So that's a P form, or Q form, K form. That's a differential form. Why is it called a differential? Well, because there are these differentials. Okay, you can also look at this as a functional on vectors, like one form is a linear functional. This will be a multilinear functional. So the form is a multilinear functional. In other words, if you take Q vectors, then it will give you a number. This is a number. Okay, how do you compute this number? Well, you take the components of that. Remember how we did it for one form? We just multiplied components and sum of it. And then you have the components of those vectors. Well, and there is sum of all I, with one restriction. Well, because this is completely antisymmetric in all indices, right? It doesn't make sense to sum over all i's, because if you switch to indices, well, that's the same component. That's why when you sum forms, then you sum actually, because it is antisymmetric, two indices cannot be the same. So you have alpha, well, I, J, M. So if there are two equal indices, then that's equal to 0. Right? Why? Because if you switch them, you should change sign, and because of that, it must be 0. So which means that in a form, all of these are different indices. And if they're different, and you could reorder them any way you want, because the only thing that changes is sign, then you can always order them in such a way that they are in increasing order. So, and then summation will go, well, I1 less than I2 less than IQ. Well, that's less or equal than n and greater or equal than 1. So, whenever you have forms, it's always summation over indices in increasing order. Is that clear? So the number of independent components are greatly reduced by this antisymmetry. Is that clear? Well, let me give you an example. Let's say you have two forms.
So should there be an factorial in there, or?
Well, if you don't have that restriction, then you would get 1 or Q factorial. Well, then it is.
Okay, I see.
So if you don't like to write this sum, then you could leave it this way, which means that you sum over all indices, but then each term will come Q factorial times. That's why you divide by this. Q factorial is exactly the number of permutations of Q indices. So that's why some of people, like including myself, like to write this way. But you should understand the origin of that Q factorial. So it's basically summing only over independent components. So for 2, 4, we have alpha ij, and it is antisymmetric, right? So how many independent components does it have?
Wait, does it matter how many dimensions it is, or?
So you have a matrix which is antisymmetric. How many independent components does it have?
N times n minus 1 over 2.
Over 2, yeah. So it is n times n minus 1 over 2. How do you get that number? Well, this is actually n choose 2, right? So you choose 2 indices out of n, and that's the number. Of course, if you change the order, so the independent ones only, the order doesn't matter. Well, if you write that matrix, then on the diagonal you have zeros, right? So the non-zeros are here in the upper triangle and the lower tier, but these are equal to negative of those. So how many are here? Well, the total number is n squared, and then you subtract n because that's how many there are on the diagonal, which is 0. And then you divide by 2, because these are equal to negative of those, and that's exactly this number, right? And so if you want to do that, compute this, then, well, let's say n is equal to 3, like in 3 space, then that number is equal to what? 3, right? So then you have, what are you can just list them. Alpha 1, tell me which ones are.
Alpha 1,
1, 2, alpha 1, 3, and alpha 2, 3. So these are the only ones that are independent. So you see that I wrote them in increasing order. And therefore, when you have something like this, alpha x, y, then that will be that. So you'll have alpha 1, 2, x1, y2, plus alpha 1, 3, x1, y3, plus alpha 2, 3, x2, y3. That is this sum. Of course, you can write it 1 over 2 factorial, which is 2, alpha ij, xi, yj. But here you sum over all ij, you will get alpha 1, 2, and then alpha 2, 1. But that's the same term, that's why you divide by 2. So each of these, we have alpha 1, 3, and then 3, 1. And that's why there is that 1 half. But if you write them explicitly, then just with the coefficient equal to 1. Okay, so that's K forms. Now, how do we define exterior product? So what is an exterior product? Well, the exterior product is, well, you have a, let's say a P form, and you take and you have another, which is Q form, and you take exterior product, so that will give you P plus Q form.